So we've spent a long time summarising linear models at a general level and sort of housing some examples within ANOVA, which is hopefully a test that you're all familiar with or that you've maybe even studied in depth in previous research methods modules. What we're now going to go on to look at is beyond ANOVA. We're still in the same family of linear models. So your t-tests, your ANOVAs, your linear regressions, we're all still in the same family, but we're starting to move now to the slightly distant cousins. And the first one we're going to talk about is analysis of covariance. Now, what we can do with our analyses, with our linear model, is we can enter a covariate and we can see what effect what effect our predictor has after we adjust for the influence of the covariate. And in the week 6 practical activity, this is what we're going to do practically. We're going to conduct an analysis to see the difference between a simple ANOVA and an analysis of covariates using the exact same data set. Why do we do this? Well, one reason we do this is to reduce within group error variance. So if we run a simple ANOVA, we get an estimate of the variance explained by the experimental factor or the predictor, and we get unexplained variance, which is typically called error. However, if we plug in a covariate, what we might be able to do is redistribute or reattribute some of this previously unexplained variance. So we essentially reduce the error variance because we explained some of it using a covariate, and therefore we more sensitively address the difference between our group means in terms of our predictor. It might be that we also help to eliminate confounds. So in any study, there may be unmeasured or uncontrolled or even uncontrollable variables that might influence our results. So what is really important to consider if you're thinking about analysis of covariance is that these variables have to be known to influence the outcome variable. So for instance, if we were looking at weight as an outcome variable and height as a predictor variable, we couldn't plug in intelligence as a covariate because there is neither a theoretical nor an empirical association between intelligence, height and weight. When you perform your literature reviews, you should justify the inclusion of these covariates. So again, a lot of people get into sort of bad practice when it comes to ANCOVA, and they essentially look at their data set and think, okay, I'm going to start plugging in covariates to see what happens. And this kind of fishing expedition is really, really bad practice. And it can lead to sort of spurious findings, and it can lead to real world problems depending on the applicability of the data. So if you're thinking about, okay, I've got a predictor and I've got an outcome, however, I've also got some covariates, justify that at the start. So, maybe that's even in a research proposal, and certainly you would review the relationship between the covariates and the predictors and the outcomes as part of your literature review / introduction. Try not to get into the habit of thinking of ANCOVA as controlling for the covariate. That's a bit of a myth. And the assumptions that are associated with ANCOVA are the same as with any general linear model. So there are also some additional considerations, such as the independence of the covariate and the treatment effect. And if the covariate overlaps with the treatment effect, there's a big problem. So the experimental effect would be confounded with the covariate in that case, and the covariate would reduce the experimental effect. It's basically stealing some of its variance. And the treatment effect would be partially obscured. You could also end up with spurious treatment effects, or at the very simplest case, your interpretation of the ANOVA is really, really compromised. It may be the case that your sort of treatment groups, your experimental groups, actually differ on the covariate itself. And this is where this idea of controlling for or balancing out the differences is misleading. So for instance, if we were doing a study on anxiety and depression, these are really, really closely related. So for instance, if we were to compare a group of anxious or non-anxious individuals on a task, there's a good chance that the anxiety group are also going to score higher on something like depression than the non-anxious group. So in this case, we couldn't simply add some sort of metric of depression as a covariate, because the effect of that covariate, i.e. depression, is going to overlap with some of the variability from your between group effect of anxiety. So we have to be really quite careful in what we consider as a covariate in relation to our experimental manipulation. Similarly, age is often flung in as a covariate, but it might not be appropriate to do so. For instance, your experimental groups might actually systematically differ in age. How can we get around this? Well, we can look at things like randomised control trials, or we can try to match allocation to groups based on some sort of covariate measure. So we have to think about our independence of our covariates and treatment effects. We have to think about the homogeneity of the regression slopes. So what we're assuming is that the relationship between the covariate and the outcome is true for each group of participants. And if we were to plot each group of participants separately with the covariate on the y-axis and the outcome on the x-axis, then the two slopes, the two best fit regression lines, should look pretty similar. However, if there is a bit of difference in the regression slopes, this is not always a bad thing, and we're going to revisit this in our next session on multi-level or mixed effects modelling. The next thing that we consider is that the multivariate analysis of variance, because so far most of our discussions has been around linear models predicting a single outcome or a single dependent variable. Please excuse the typo, that should not say IV. If we are interested in several or multiple outcomes, we can use multivariate analysis of variance or MANOVA. And what can we do with MANOVA? Well, we can use this when we've got either one predictor and multiple outcomes. Sorry, again, that's a typo. That should say multiple outcomes and DVs. We can use MANOVA to examine interactions between outcome variables, or we can use MANOVA to examine which groups differ via contrasts. So univariate general linear modelling is when we have one outcome variable. Multivariate general linear modelling is when we have many outcome variables. You might be asking yourself, why don't we just do a whole bunch of ANOVAs? So if we've got the same kind of design in terms of independent variables or predictors and their levels, and we've got lots and lots of different outcome measures, why don't we just run a whole bunch of ANOVAs? And a lot of researchers do this. So for example, if I've done a study on eye movement behaviour during reading, I've maybe got lots and lots of different measures of that, and instead of maybe looking at a MANOVA, I've performed a series of different analyses of variance. Similarly, if you're looking at cyber abuse, if you have manipulated, say, the valence, the emotional content of an initial post, and then measured responses to that post and how it impacts on things like attractiveness, victim blaming, perceived severity, why not just do a whole bunch of separate ANOVAs? Well, when you carry out lots and lots of tests on the same set of data, you actually increase the likelihood of making one of these type 1 errors. And furthermore, the separate linear models, maybe for example separate analyses of variance, will actually neglect the relationship between different outcome measures. However, that is not to say that we can just simply go fishing and say, right, I'm going to run a MANOVA because I've got all these different outcomes. You have to have a good theoretical or empirical basis for combining these different outcomes, these different dependent variables in a MANOVA. Don't just fling everything into the soup. So in some cases, it actually is better to do these separate ANOVAs, these separate linear models, unless you have a really solid justification for performing the MANOVA. Again, like its cousins across the family of linear models, most of the assumptions are very, very similar. There are some additional ones, so independence, so the residuals should be statistically independent. Random sampling, we should have tried to randomly sample and have data measured at an interval level. We should have multivariate normality of residuals, and we should have homogeneity of covariance matrices. We're not going to talk about this in detail just now. We'll revisit this in week 7 in the practical session. And again, in univariate models, we talk about homogeneity of variance, maybe across levels of our predictor or our IV or across groups. And in multivariate models, what we're really looking at is the correlation between any two of our outcome variables and making sure that that correlation is the same across all groups. So it's a very similar principle, just extended across these multiple comparisons. If we violate assumptions or if we have bias, if we are planning to do a MANOVA, we can correct for this in a similar way to as in univariate models. So we can check univariate normality for residuals for each outcome one at a time, and this is practical, it's useful, but it doesn't actually guarantee multivariate normality. So you might want to consider using something like a boxes test. And again, I don't want to get into the mathematics of this, but essentially it's a bit like a Levene's test, but extended to look at multivariate analyses. And again, what we're looking at here is making sure that we have equivalent variance across predictors and across outcomes. This is a bit of a problematic test. It's sensitive to deviations from normality, and large samples can actually cause a problem driving a significant result. Remember earlier on when I talked about sample size? Bigger is not always better, especially if you go to extreme sample sizes. So we have to think quite carefully if we're performing a MANOVA or trying to interpret a MANOVA about our assumptions. Having equal sample sizes and equal numbers of observation across your outcome measures is really, really important. And again, if you're really, really interested in this, you can follow up by looking at things like Hotelling's tests and Pillai's tests as well. We're not going to cover that in this session, but I'd be happy to discuss those individually. We're going to recap now with some of the take-home messages. And that is that we should stop trying to see things like t-test, ANOVA, regression, ANCOVA, MANOVA as being very, very different from one another. They are all part of this family of general linear models. ANOVA is a really useful tool for investigating relationships between predictors and outcomes. Let's not lose sight of the fact that ANOVA is still a really, really good statistic if used appropriately. ANCOVA can be really, really helpful to adjust the effects of your predictor or your experimental factor based on the effect of an uncontrolled covariate. But it's still better to try and use true random allocations to conditions or to pre-test to assure equivalence across groups rather than simply banging in covariates into some sort of model of the data. MANOVA is kind of difficult to follow at a mathematical level, but the crux of the matter is that if you have a solid theoretical or empirical reason for incorporating lots and lots of outcomes or dependent variables into a single model, as opposed to conducting separate univariate models, then by all means consider this multivariate analysis of variance, which in turn could help you protect against type 1 errors. I'd like to say thank you very much for listening. I hope that you found this useful, and as I said, I'll be happy to follow up with you either by email or in person, and I hope that you look forward to the practical activity which is based around executing an ANOVA and then following up with an ANCOVA so that we explore the role of these covariates in estimating the effects of our predictors or indeed independent variables.